An important application of modular arithmetic is the so-called RSA cryptosystem. Here, we want to set up an encryption system so that anyone can send you encrypted messages and only you can decrypt it. First, we need a set of rules of converting between words and numbers. A simple way is to correspond the letters A to Z to the numbers 1 to 26 in the alphabetical order. We also want to make sure that the numbers have the same number of digits to avoid confusion. So we would add 0 to the numbers 1 to 9. So the letter A corresponds to 01, B corresponds to 02, C corresponds to 03, and so on, until Z, which corresponds to 26. Using this set of rules, the word maths corresponds to the string of numbers 13, 01, 20, 08, 19. To set up the system, I will publish two numbers, 55 and 3, which is called the public key, and I will explain the choice of these numbers later. Everyone can see this key and use it to send me messages. I have another three numbers, 5, 11, and 27, which is called the secret key, and I will keep them secret for decryption. The process of encryption is as follows. Suppose someone wants to send me the message 7, which means G. To encrypt, this person needs to compute 7 cubed mod 55. Here, 7 cubed is 343, which is congruent to 13 mod 55. So the encrypted message is 13, or M, and this is the message that I receive. As for decryption, I should compute 13 to the 27 mod 55. We shall proceed using successive squaring. We write 27 as 16 plus 8 plus 2 plus 1, and compute these powers of 13 one by one. 13 squared is 169, which is congruent to 4 mod 55. 13 to the 4 is congruent to 4 squared, which is 16 mod 55. 13 to the 8 is congruent to 16 squared, which is 256, which is congruent to negative 19 mod 55. 13 to the 16 is congruent to the square of negative 19, which is 361, which is congruent to negative 24 mod 55. So, 13 to the 27, which is 13 to the 16, times 13 to the 8 times 13 squared times 13 is congruent to negative 24 times negative 19 times 4 times 13. This product is 23712, which is congruent to 7 mod 55. So I have retrieved 7, which is the original message. After seeing the process of encryption and decryption, let's talk about how to generate the keys. As the first step, we need to pick two primes. Here, I pick P equals 5 and Q equals 11 to get the public key in the previous example. In practice, these prime numbers should be super large, say greater than 2 to the 500. Secondly, we compute the product of these two primes, which we call n. So in this case, n equals 5 times 11, which is 55. And we have the first number in the public key. The third step is to choose an encryption key, say E, such that the HCF of E and P-1 times Q-1 is 1. In this case, we need the HCF of E and 40 equals 1. So E equals 3 works. The numbers n and E form the public key. The fourth step is to compute a decryption key, D. By the congruence equation, D times E is congruent to 1 mod P-1 times Q-1. Here we know that D must exist because the HCF of E and P-1 times Q-1 is 1, and this is a result from the fourth video. So we need 3 times D is congruent to 1 mod 40. Using the extended Euclidean algorithm, we can write 1 equals 40 minus 3 times 13. So d is negative 13, which is congruent to 27 mod 40. We now have the secret key, which are the numbers p, q, and d. To explain why the system works, let x be the encrypted message and y be the decrypted message. So y is congruent to x to the power e mod n. It suffices to show that x is congruent to y to the power d mod n. Since d times e is congruent to 1 mod p minus 1 times q minus 1, there exists an integer k such that d times e equals 1 plus k times p minus 1 times q minus 1. Now, y to the d is congruent to x to the e to the power d, which is congruent to x to the power d times e, which is congruent to x to the power 1 plus k times p minus 1 times q minus 1. We can write this as x times x to the p minus 1 to the power k times q minus 1. Using the Fermat's little theorem, we know that x to the p minus 1 is congruent to 1 mod p if x is not congruent to 0 mod p, and is congruent to 0 mod p if x is congruent to 0 mod p. So y to the d is congruent to x times 1 to the k times q minus 1 mod p if x is not congruent to 0 mod p, or y to the d is congruent to x times 0 to the k times q minus 1 mod p if x is congruent to 0 mod p. In neither case, y to the d is congruent to x mod p. Similarly, y to the d is congruent to x mod q. Now p divides y to the d minus x, and q divides y to the d minus x. Since the HCF of p and q is 1, from a result in the second video, we know that p times q also divides y to the d minus x. In other words, y to the d is congruent to x mod n, which completes the proof.